continue to use the OneNote. Okay. Okay. So are you able to see this OneNote that I have shared?
Yes, yes.
Okay.
Yes, sir.
Excellent. Okay. Yeah. So hello everyone, welcome back to the EC 101 classes. Okay. So I hope the tutorials conducted by Shoaib and Tanveen have been helpful. And if you are not able to attend those, please watch the videos on the YouTube link I had already sent, the channel link I had already sent. Okay, and it's also there on the canvas. The link to the YouTube channel is also on the main page, or landing page, I think, of the canvas as well. That way, even if you forget the link, it must be there. Okay.
So the keyword axis that we were doing in the last week, the plates that we made, that did not result well. Also, so then we also tried the 3-way stop curve. It is starting. That's like yes. So also the 3-way curve thing, that did not work. So that did not work. Basically, we think that we are
Somebody
adding
You have
the
to
has
mute
joined
those,
here,
sir.
and
there might be some
You
gap
have to
in the
mute
middle.
them.
So they are not in
Arun, can
actual
you mute
contact.
everyone?
So the cells did
Yeah,
not
you can
move
mute.
at all. So
Arun.
it cells in the place where the
all the
media
please mute yourselves. Okay. Yeah. So I think let's start now. So last week we were discussing the basic question of how populations change over time. Oh, sorry, this is really horrible. It's still quite thick. So how populations change over time? That's the question we are interested in. To understand this, we need to understand the processes that influence the population size, right? So those processes are birth, death, migration, and then we also discussed issues like resources,
Immigration.
and so on. We made a whole bunch of lists, diseases and so many other factors. So the basic idea is that one way to think about this is, which of the processes are most fundamental, right? So which are the processes that actually contribute in the direct way? And if you think about those are basically birth and death. Resources affect birth and death. If you think of diseases, they affect birth and death. And if you think of competition, they affect birth and death, and so on and so forth. If you think of the processes that directly contribute to change in populations, so those are basically these three, and of course one can add a few more if you think more. What does an isolated population mean? A population that is isolated from the other populations. For example, think of an island. Let's say I want to study a tree species and how it's changing over time in an island, or it could be a small mammal, or it could be any animal I'm interested in, and let's say I want to study how that population is changing, but over an island. Why do we make this sort of a simplification? Because by doing so, we can assume that the seeds can disperse via water currents. from another island or the sort of bigger mainland, and also the reverse can happen. There could be emigration just because of the fact that you are an island. We have to assume that it's an island which is sufficiently large. Okay, so if we assume that we can ignore one more term from the list of processes, so therefore if we understand how the birth and death are changing over time, so we have a reasonable sort of we can now try to sort of account for how the populations change over time. Okay, so let's do that. Let's do under a fairly simplistic scenario. Okay, okay. So that means if you were to ignore migration, you can write the following, right? Let's have a simple notation. N subscript t stands for number of individuals in the island or in the isolated population at time t. Okay, now let's say we want to know what is n of t plus 1. What is 1? You can think of 1 unit of time as equal to 1 generation, because 1 generation is a reasonable time scale where birth and death happen. So this could be as small as 20 minutes for various bacterial and cellular populations, but it could be as long as a century if you are thinking of some very long-lived mammals. Okay, so now what is nt plus 1? What, given that I know that there were some individuals at time t. Okay, now so n of t plus 1, the number of individuals in this population at time t plus 1 depends on what was there at time t, right? Okay, so there was some population that was at time t, and there were a whole bunch of birth events in this duration of 1 generation, and there were also deaths. So if I know the previous population and the births and deaths that happened in this 1 generation, I will know the next population size. Okay, so let us now, so we don't therefore need to find out what's the total number of births and what's the total number of deaths that happened in this 1 unit time of 1 generation. So how do we know? So let's try to make some reasonable estimates for what is that going to be. So let us assume that on an average, every individual will have R number of offspring. Okay, assume that we have R0 offspring.
Oh, audio driver ಹೋಗಿದೆ.
Per individual. Okay, now and let us also make, so that will now help us find out what's the total number of births. What would that be? That would be R0 times nt. Is that fine? Okay, so there are nt number of individuals, and each of them produce R0 offspring, and therefore the number of births will be R0 times nt. So likewise, what about the deaths? What are the number of deaths that have happened in this period? Let's assume that d is sort of probability of death per individual per generation. Okay, so if you then you can now make a sort of an approximation that number of deaths will be d times nt. Okay. So there are basically R0 times nt number of births, and there are d times nt number of deaths. So if I now put these together, what do we get? We get that the number of individuals at time t plus 1 is equal to the previous generation size nt plus the number of births. Let me just remind and write the equations again. minus deaths, right? So nt times r0 times nt, that's a number of total number of births, right? And the total number of deaths will be d times nt. Okay, so now I can simplify this equation and write this as nt plus 1 is equal to, I can take nt as a common factor and write 1 plus r0 times t times nt. Okay, and then I can simplify this further and say r times nt. Where r is equal to 1 plus. So I have chosen a not the best notation possible, like maybe we should have called b maybe b as the number of offspring instead of r0, but anyway I'll stick to this. You should feel free to change in your notes. Okay, so now we have a sort of given that I knew what was the number of individuals at time t, I am now able to compute or make an estimate of what the numbers will be in the next generation, where this basically turns out that the nt plus 1 is nt times a multiplicative factor r. What is r? R is 1 plus the number of births minus number of deaths. Okay, so now let's, whenever you have a simple equation or any equation of this type, you must first try to make sense of what are these parameters stand for and what are the numbers, what are the possible numbers these parameters can take. Okay, let's just think about that a bit. So what are the possible range of values that r0 can take? So r0 is the number of offspring that an individual in the previous generation produces, right? What's the possible range of values that r0 can take? Can somebody answer this question? Try to guess.
Greater than 0?
Okay, it has to be greater than 0, absolutely right. Because it's a number of births, right? So
Can be natural number.
r0 has to be greater than 0. Oh, sorry, greater than 0. Okay. So the another answer I get is it has to be a natural number. Does it have to be a natural number?
No, right? It's some kind
No,
of
actually.
average.
So it's an average number. I did not make it very clear when I was saying, somewhat intentionally. So r0 need not be a natural number. It could be it could be a real number. It has to be a real number, of course. But it doesn't have to be a natural number. Okay, so r0 has to be greater than 0. R0 can be real number. Okay, or if you are a mathematician, you will write something like this. Sorry for the repetition in R. Maybe a curly R. If I can manage it. What else? Is there an upper bound for R0?
Environment, or based on the particular species in question, there might be.
Okay.
So maybe if we're talking about like species that can only rear an offspring or two, then we can say that maybe it is twice nt. Like, but that will depend on the species and on the environment in question.
Absolutely right. So it depends on species ecology and environment. Right? Okay. Okay. Absolutely right. So at least we know that R0 is a positive number. What about D?
0 to 1.
0 to 1.
0.
Absolutely right. Can it be more than 1?
No.
No, right?
Probability, right? Can't be.
It's a probability. And then if you also think of the total D NT being total number of deaths cannot be more than NT, right? So D has to be necessarily between 0 and 1. Okay, so which means, okay, I'm going to make some small space here. So put these together. What's the range of values that? Oh, sorry. What's the range of values that R0 can take? Or sorry, not the R0. R. R0 can go from 0 to some upper limit. Okay. Some, that depends on the, the species. Let's call it maybe Rm. Okay. Let's denote this as Rm. Maybe in fact I should Rm. Okay, maximum or maximum. So R can go from, what's the minimum value R can take? Minimum value is when R0 is
R.
minimum
So
and D is
0.
maximum, right? So R0 minimum is 0, whereas D maximum is 1. So in which case it will be 1 plus 0 minus 1. So R itself can go all the way from 0 to, what's the
R.
maximum value that R can take?
We just said R0 will be greater than 0. It is strictly greater than 0
Yeah.
initially. So R can also be only strictly greater than 0, right?
Is that fine?
Okay, then it's fine.
Okay, so R goes from 0. What's the maximum that R can take? When R0 is maximum, which is Rm, and D is minimum, which is 0. So it's basically R0 plus 1 is the maximum we can take. Rm plus 1, meaning there are no deaths and the species is reproducing at the maximum possible capacity. Okay, so those are the ranges that these parameters can take.
So I had two questions. So in case of species that lay eggs, for instance, when do we consider a birth? Is it the laying of the egg or is it the hatching of the egg?
It's actually a very, very good question. I haven't at all made clear, right? And it is not an easy question to answer. So I will let you think about that. It's a very, very good question. What's your name? Say your name again. Who asked the question? Nilay, right? So Nilay asked this question. Let me just rephrase it for everyone. So how do you, if you were to really go on, let's say if I've given you some organism but I have asked you to experimentally determine R0, what do you do? Do you look at the number of eggs? Do you look at the number of offspring that actually hatch from eggs? Or is it even more? How do you really measure R is the question that he's asking. It's actually a very interesting question. Do think about this. I won't answer it right away. Do think about this question. Okay.
And so my other question was, okay, we can establish that a birth counts in R0 and a death counts in D. But what about postnatal deaths? If there is any incident of postnatal deaths, wouldn't that kind of allow for D to exceed and not NT?
So again, it basically is a question of how do you define? There's somebody who is switched on talking in the background. Is it possible to find it around who is that? Is it a sort of somebody who has sort of gotten the link accidentally? Okay, that sound is gone now. Okay, so if you have my sincere request is please don't there are two things. If you're in the class, I'm assuming that you're actually listening and not doing anything else. Therefore, even if the mic was accidentally on, I shouldn't hear too much noise. So anyway, independent of that, please, there might be other people around you who might be speaking. So please switch off the mic unless you're trying to ask a question. Okay. So yeah, so it's a great question again. D is the, if you look at the definition carefully, which of course probably we didn't define very, very carefully. I wasn't very careful in defining a lot of these things. Probability of death of individual in the generation T. Okay. I'm really looking at the death of one of the guys who are in this NT. So postnatal deaths, by which, if I understood correctly, you mean that somebody is now born, egg has been hatched, somebody is born, but someone dies after some time, right? Is that what you meant by postnatal deaths?
Yes, sir.
That doesn't quite apply to that D then doesn't actually apply at all, right?
Okay.
D is for somebody in the generation T. Okay. So, if you think through this carefully, you can define all of these terms carefully. So basically, because you have asked this excellent question, let me just answer this a bit more. So when we say NT, what exactly is NT? Is it, if I think of, let's say, bacterial population, probably NT is everyone in the entire population. Okay. However, if you think of, maybe insects, okay, then NT at the maximum can be NT. You can't include both male and females. That would be unnecessary double counting and not useful for our calculations. Because imagine if everybody was a male, then NT would be still 0, right? If everybody was a female, it would still be NT is effectively 0 again, right? So, so you have to now define what is NT in your population. Okay, so one can say that NT, I will take it as number of females, assuming that there are sufficient number of males for mating, without bothering specifying what that number is. There are sufficient number of males available for mating. Therefore, I'm now going to keep track of only females. So therefore, the NT becomes female population size. And then if you now think of NT, it's not just in that generation, the NT might be slightly fluctuating over time, right? So NT is technically the adult population who can actually reproduce.
Okay.
So NT actually is not only female population who are actually adult and they're actually ready to reproduce. So which means that when I'm now saying births, the birth, now if you keep this in mind, because I'm only calculating NT plus 1, which should be what I'm trying to estimate is, given this adult population of females in this species, what will be the adult female population in the next generation. So which means that I am not only looking at, if it's a case of, let's say, egg producing organism, X, it's not the X, R0 doesn't represent X, R0 doesn't even represent the number of eggs that I've hatched, R0 doesn't even count the number of juveniles. It actually counts the number of juveniles who actually survive to become adults per individual.
Okay.
Right? So, so that I think will clarify what exactly R0 and T stand for, and both of them are defined for a single generation time scale. Okay.
Yes,
Thanks for this question. That I hope clarifies. Maybe not fully, but to some extent. And this, what exactly is also relates to the a very important question also, which comes probably later. May not be in this course in a very strict sense, but it's a very important concept. Which how do you define fitness? Fitness is a concept that will come again and again in biology. But how exactly do you define fitness? It's also a question that relates to what exactly is R0. And it's a tricky definition. It's actually very tricky to define what exactly is fitness, depending on where exactly you are closing the life cycle. Okay. Okay. So now we have done this. So we have this equation, which is, I just changed the color. Not R. N f t plus 1 is equal to R times N of t. Okay. So now, this is what we have arrived at. Let us say that, if I now do a back calculation, can I make connection between NT minus 1 and NT? I'm getting NT plus 1 by this multiplying NT from a, from a number R, which was 1, which included birth and death processes. Likewise, let us do the same, apply the same rule for NT and NT minus 1. Okay. And if I now do this and if I simplify the equation, what do I get? I get NT plus 1 is equal to R square times NT minus 1. So what I have,
we are assuming R remains constant across all generations. That need not.
I have right now assumed that R remains constant across 2 generations. Is that right?
Yeah, but is that a viable assumption?
Great question. So I will let you think about that. Okay. That relates to the assignment I'm going to give you very soon. Okay. So if I do assume that R is constant across 2 generations, I can write this. And how did I get this? Basically, what I have done is, in this equation, I have replaced NT by this expression in the second line. Okay, say this is A, this is B. What I have done is in A, I have substituted NT from equation B, and therefore I have this equation C. Okay, and
So would that be a T minus 1?
T minus 1.
oh,
Yeah.
I'm so sorry. Yeah, that obviously is T minus 1. Thank you. Okay. And let us, for the sake of argument, assume that we do this for all the generations starting from the 0th generation, and sorry, first generation. Okay, so let's say somebody had given me a population n1 in the beginning, and if this assumption that R is constant across all generations, R is equal to 1 plus R0 minus D is constant over. This is a very, very crucial assumption. It's true, we can arrive at this expression that connects NT plus 1 with the very first generation I had. Is that fine? Okay, so for those of you who have not done this kind of calculations, just try to apply, basically what is the intermediate stuff. Now what you do is basically make a connection between NT plus 1 and NT minus 2 with this equation. Sorry, NT minus 1 and NT minus 2, and then go back to this equation. You get one more equation that connects NT plus 1 to NT minus 2. You keep on doing this and until you reach the first generation, and if you do this, you get this expression, which is NT plus 1 is equal to R power T times N1. Okay, and of course this relied on this really, really crucial assumption that R has been constant across all the generations that I have been keeping track of. Okay, so let us now look at the implications of this if this is true. Okay, so what does this? What are the implications if this is true? Okay, so let's look at, write down the such a horrible handwriting. T plus 1 is equal to R power T times N1. Let's consider a few cases. As we figured out, R is a real number between 0 and some maximum limit. Let's consider two cases, rather three cases. Case 1, when R0, R is actually less than 1. What does this correspond to? Remember that R is equal to 1 plus R0 minus D. If R is less than 1, what does that mean? R less than 1 means that this entire right hand side is less than 1. 1 plus R0 minus D is less than 1. So 1 and 1 cancels. What that means is R0 is less than D. So case 1, the scenario I'm considering basically means that R0 is less than D. Remember the definitions of R0 and D. R0 is the number of offspring per generation per individual, and D is the depth of the individual, right? Which means if the number of offspring produced by an individual on an average is less than its own death rate, what's going to happen? I'm sure you can make an easy guess. If my death rate is more than the number of offspring I'll produce, if everybody is like that in the population will probably do what? Go extinct.
Extinction.
Right? Now, indeed, that's the case, because when R is less than 1, RT goes to 0 as T goes to large numbers. What that means is that NT plus 1 goes to 0, and this happens independent of the value of N1. Okay, so there we have basically a case of extinction of population. Okay, so that's one case. Let's look at more cases. What's the next case that you would want to probably look at?
Greater than.
Greater than. Let's do one more in between. So this is 6. Let's also do a case
0.
r is equal to 1. So if I now do the algebra again, this basically will correspond to R0 is equal to D. Okay. Which means the number of offspring per individual per generation is equal to its own death rate. Okay. So what do you expect in that case? Of course, RT will be 1, right? And therefore NT plus 1 will be same as NT and 1. So the population basically hasn't changed. Remains constant. And so in a and that makes sense, right? The basically whoever is dying is equally being replaced, and therefore the population size doesn't change over time. Let's now look at case 3 when R is greater than 1. This basically will correspond to the number of births per individual is greater than the number of deaths. What do you expect in this case? RT will now goes basically towards infinity because R is a number greater than 1, right? And R power T will be an exponentially growing function, right? So therefore, NT plus 1 will go to basically, infinity should be used in quotes here because you will never really have true infinities in biological worlds as time becomes large. So a more sort of reasonable way of saying it is in the case when R is greater than 1, we basically have this expression of RT is equal to, NT is equal to R power T times N0. This is basically an exponential growth of populations. Okay.
So R power T or R power T minus 1?
What did I write in the previous slide? Okay, so NT plus 1. Okay, I think I have changed my notations a bit. So I was connecting between NT plus 1 to N1. What I have done here is I have connected between NT and N0. So they are both basically equivalent statements, right? Do you agree? So I start with some population N0 at 0th generation. I have just named them a bit differently now. Then the NT will be given by R power T times N0. Is that right? And that is exactly same as this equation. Is that fine? If it's confusing, I can sort of go use the previous one.
So the R is from like T and N is T plus 1. So here I think it should be RT minus 1.
So basically one way to think about what should be the exponent value is look at the difference between the subscripts. Okay, it's T and 0. T minus 0 is T. Okay, and here it's T plus 1 and 1, and the difference is T. Is that fine? So the exponent must be basically the difference between this time unit and this time unit. So for example, I could also have written somewhat arbitrarily that NT plus 2 is equal to R power T times N. Is that right? This and this are equivalent. So basically, one way to think about this, here if I replace T by T plus 2, but I have correspondingly then so I hope it's clear to why these two are the same. Or is it not clear to some people?
Clear, sir.
I mean, I can understand it may not be clear to some people. That's totally fine. But just if you try to go back and derive this the way I have done here, you will be able to make those connections yourself. So you can basically make connections between, let's say, kth generation population size and another, let's say, tth generation size, entirely based on the difference in generation times, under the assumption that this R is constant across all generations. So if you assume this, you can actually write down an expression that connects any two generation population sizes in any two generations, and maybe you could even think of it as a small exercise that generalizes the calculation in this, in this slide.
Sir?
Yeah.
With respect to like RM that you had mentioned as the upper limit of the species, like the in the birth rate. So in that I had one confusion. That is not considering the carrying capacity of the environment. It is just considering factors like gestation period, etc. Right?
You are right, absolutely right. I haven't. In fact, whether I have considered or not. Let me see if I did consider it or not. Okay, I wrote RM as an upper limit, depends on the species and environment, right? Don't you think it does account for the fact that environment will have some limitations that the species will have to account for, right? So environment
But if
is
you're taking-
imposing, so I have considered the fact that it does depend on species, biology, and the environment.
But if
this
you're taking
RM should
that,
be
then that will, sorry, if you're taking this environment factor, then won't that bring into account carrying capacity and other factors also?
It will. So RM can depend on the carrying capacity. Absolutely, yes. Which is why I have written environment. Absolutely right. Yes, yes. It can depend on that. Is it fine? Okay. So let me now.
Actually, I had one confusion because like the RT was tending to infinity, right? So won't that get limited if we are considering the carrying capacity factor?
Absolutely, yes. So that's the question I'm actually going to ask you now. So what have we done so far? Let's go through this, right? We started with the number of individuals at some time t, and we were trying to sort of see how this population progresses over time, right? And then we wrote down this expression: nt is equal to nt plus 1 is equal to r times nt, and then based on the assumption that r is constant over generation, we wrote this expression that connects the population size at t plus 1 and 1. Okay, and we have now studied three cases. What if r was less than 1? What if r was equal to 1? And what if r was greater than 1? We have considered all the three cases, right? Okay, now we have basically found three possible outcomes. When r is less than 1, we have extinction of populations. Do you observe those in the real world? Yes, we do observe extinction of populations whenever the reproduction rate doesn't compensate the death rates, and in fact populations where R0 is less than D, they're often also called endangered species. Okay, and we also considered the case R is equal to 1, where the births and deaths are absolutely equal, and therefore the population doesn't change at all over time, right? And now we also consider the third case, when R is greater than 1, and then we found the implication that this will lead to an exponential growth of populations. Okay, now as you are rightly saying that if you were to plot this, the third case, let's just plot all the cases. Okay, time and n. So there was three possible cases. One is that of, let's say this was the population size at time 1 unit or 0 unit. Let's just call it 0 and 0. Okay, if R0 was less than 1, what we find? We will find that the population decays exponentially. If R0 was 1, we will find that N0 doesn't change over time. Okay, and if R was greater than 1, what do we find? We find that the population will increase exponentially. Okay, so we can also write down the cases. This is R less than 1, equal to 1. Okay, I think I was saying the notation strongly. Must be capital R less than 1, equal to 1, and greater than 1 scenarios, right? Okay, so we are only finding 3 scenarios here according to this: a constant population that doesn't change over time, and a population that just goes extinct, and a third scenario where population is just increasing forever exponentially, right? Now we all know that, can this happen forever? Can the population keep on increasing forever? As somebody just rightly pointed out, environmental constraints will begin to play a role, right? So clearly this cannot happen forever. But can this happen at all? Can populations grow exponentially at all?
Not
Yes.
really, right?
They can. And when is that?
When there is no resource limitation.
When there is no resource limitation, right? But they can, increase forever. Now here is the question I'm going to ask you. So don't answer the question right away. You don't need to answer the question to me, because I'll first get the question. So we wrote down an equation for population, right? Under the assumption that R is equal to constant across all generations. And therefore we arrived at an expression which is nt plus 1 is R times n1 power t. Okay, and of course we started off with a much simpler equation, which is nt plus 1 is equal to R times nt. This is how we started off. Now, can you now write down an equation for how population changes over time, accounting for resource limitation? Here is the question I'm actually asking. Okay, how will you write down an equation for how population change over time, accounting for resource limitation? Now this might of course be a very daunting exercise to do, right? So I'll try to simplify the problem to you a bit. So you wrote down an expression of this type, right? R times nt. Okay, so this we all agree is right for one generation. Do we all agree this equation is right? Do you have a problem with this, at least for genetic physics for one generation?
No.
You are all happy with this, no? Now here is the question: how will you modify this equation that accounts for this? That's what I would like you to think. You have seen that, if I apply this equation recursively over time, I'm always going to end up with these 3 scenarios, right? A very trivial scenario of extinction, and an extremely trivial scenario of a constant population size, or another extreme case of exponential growth. Can you do something better to improve this equation that accounts for resource limitation? Okay, so now how are we going to do this? So I'm not going to answer. I'm not also going to open this for discussion anymore. What we will now do, I'm going to stop sharing my screen. Of course, I can share the question again. So I would like you to think about this question now for the next 30 minutes. So using the breakout room option we have. Okay, so what Arun will do is now create breakout rooms. I have no idea how it works, so we were doing this in a bit of experimentally here. So what we will do in the breakout rooms is that We'll be 5 people in each breakout room. I think there are 58 participants. Maybe we can make it 6 around. 58 includes me, no? Me and 2 TAs and so on. So yeah, I think 5 per room is probably fine. Okay, 5 per breakout room, and in your group, come up with a sort of a modified formulation that accounts for resource limitations. Is that fine? So how you do is entirely up to you. You have 30 minutes, and I will just ask you at the end of 30 minutes, show me the revised equation you came up with. I don't want to know the equation, to be very honest. I want to know what thought process was that you were going through. Okay, and if it turns out that 30 minutes is too short, we can extend the time for a bit more, but maybe we can start with 30 minutes as the time. Okay, Sarun, are you there? So I don't know how the breakout room works. In fact, I can actually do it myself. So, but the only thing is I don't want, okay. So Shoaib and Tanvin, you will also be moved to, I don't know how to say, the hosts and co-hosts will also create the number of, I have to create the number of breakout rooms. Okay, I'm going to make 10 breakout rooms, which means there will be 5 to 6 participants per room.
I think the
and you will all be assigned randomly. Is that fine? Okay. And Shoaib and Tanvin, whichever room you get allotted to, just do one thing. Just I think I hope there will be a way to come out. Okay.
I think yeah, we can choose not to join. Like
yeah, exactly.
You can choose not to join, but everybody else, please, we must join. Okay. Excellent. So I'm going to create now. Okay. It has randomly assigned people. I'm going to open all the rooms. So please join the rooms. I don't know how it works. So do people, does everyone still hear me? I have no idea how it works now.
No, I don't think others can hear you.
Okay.
They've already joined the room. Yeah.
Actually, you can join different rooms and interact with them if you want.
So only me, you.
Rashi is left.
Okay. Yeah, I think Shoaib was supposed to be in. Rashi hasn't joined. Okay, I think this looks good. Okay. Was my voice clear, by the way? Somebody has message saying there's a lot of disturbance from my side.
Oh, I didn't find any disturbance.
Okay. So what do we do now? How can we go and talk to people?
On the left, there are options. There's a icon, no? It says join breakout room.
Where?
On the left-hand side. Do you see 4 boxes?
No, I don't.
On the right-hand side. Like.
Okay, yeah.
I can't see anything.
It's like a dice kind of. I mean, like a square with 4 other squares.
Next to record.
I don't know. In my app, it shows like that.
Oh, are you on mobile?
Yeah, the tab.
I should use gallery. No, gallery also I don't find anything.
Or maybe there might be more option, no?
So one Priyansh has suddenly joined. How can we move into a room?
So I was in 8. I was in 8 room.
Okay, I will
8th
move.
room.
We have been assigned. Okay, now how do I join any of the rooms? I don't find the option of. Okay. I found yes.
Should we also go and roam around different rooms? Sure.
Uh,
Should we also go and roam around different
I don't
rooms?
know. What do you wish to say?
Okay, I think you go to.
Okay, we
go
should back.
Oh,
But currently people will be discussing now. So I think we can go after some 20 minutes or something. Like,
yeah. I just want to see how it is going. Like we leave.
Issue's muted. Like, we can't hear you, Ishu.
We can go and join. It's going to be fun, a lot of fun.
But we can use like silent sector right now. Okay, Tanvin went somewhere.
Should I ask them to write up something? Because it will be submitted, in the end.
Yeah.
But will they be able to write in? I just need half a page write up on what you did. Can we ask them?
Yeah. Yeah, someone should,
Yeah.
someone in the group can write and they can share it as an image or whatever.
So what would be the deadline? Today itself, no?
Yeah.
Yeah, then it should be fine. I think.
It would alter other properties. So we could account for it in birth rate and death rate. So we did that independently. So where does carrying capacity come into effect? It's if the population size is greater than the carrying capacity, at which point we need to account for the fact that the environment can no longer support it, even if the birth rate and death rate does that. And as you can see on the left side, that's the evolution of our multiple equations, where we were wondering how we can account for it, which supports what we have written down in points here. And finally, we reached the conclusion that the equation written in the bottom, I don't know if you can see it, the one I'm underlining, right? That is where we reached. So we decided to write it in this particular case and account for the edge cases, which would be if it's greater than the carrying capacity, like if NT is greater than carrying capacity, then the first term would go to 0 because 1 minus, and because this would be 1 at that point of time. So then it's NT plus 1 would just be NT when it's equal to carrying capacity, and when it's lesser than carrying capacity, we included R minus 1 because we've externally included NT. And in this particular case, we needed to mimic like 10 to this particular equation, which is what we started working with. So that's basically where we reach with our discussion. If anyone else from group 1 has to add anything, please go ahead.
Thank you.
So essentially, we just try to introduce something such that it drops down to what we began with, what you gave in the lecture, in when the population is small, and then when the population is high, it kind of caps it. That's what we try to do by introducing. That's all. Thank you.
Okay. Sounds good. Sounds good. What about the next group?
I'll stop sharing. Thanks.
Yeah, thank you.
Hello.
Group number 2. Yes.
Group number
Who
2.
is?
I'm Ankush.
Ankush. Yes, please go ahead, Ankush.
Can you see my screen?
Yes.
Yeah. So we had a different way of approaching this. So we were we kept the amount of we took the case where the resources kept getting replenished at every time interval. We took a discrete time step kind of a thing, where each individual consumes m resource units per time interval, and if the individual does not get the resource in that time interval, it just dies. So the amount of resources again is replenished by a unit of p every time unit, and in the beginning you have m naught resources at the beginning. And we also have the r naught as the birth rate and d as the death rate, this is the death rate due to natural causes and not due to starvation. So yeah, because the starvation death is taken to be as instant, because they don't get the food. So the first equation is basically the population increases.
The first is same as what we had before.
Yeah, exactly. And then we have the second equation, resource equation. So the previous resource, whatever we had at time t remains, it increases by t and then decreases by mnt, which makes sense.
Okay.
And a third equation that we could not write because of a little bit of time issues was.
That's fine.
Yeah.
So you need to make some connection between 1 and 2 though, right?
Exactly.
How does M feed back to N is in this case not done. No, okay.
Yeah.
But we're trying to do that.
Yeah. So what happens is if MT plus 1 drops down to 0 or below. So
Okay.
no, if it drops down to 0, it's fine. But if it drops down to below 0, then everything that is basically all the individuals that could not get the resource will die. So if MT plus 1 is less than 0, then the NT plus 1 reduces by an amount, which I guess can be written as. Do you need the exact?
It's fine. If this is fine. I understand the approach you're taking.
Yeah.
In a short time, it's I'm not looking for all the precision behind it. That's fine. That's very nice.
Yeah. So only the individuals that get the resource survive. The rest of them die, and and then it stagnates.
Now, what about group 3?
Yes, I'll share the screen. Vivek, can you speak?
I can't see the screen.
I can see.
So basically what we wanted to do is the growth rate, that is R, I mean the net growth rate, which will depend on the birth rate and death rate, now will become a function of the current population. That is, as the population increases, either your growth rate decreases or your death rate increases. So basically we wanted to change the function, the form of R. Now it will be dependent on N and K. Both the birth rates and death rates will be a function of N and K.
Okay, that's great. Very nice. Okay. So you have not done an explicit form, but that's the thought process.
Yes.
That's good. Okay, that's fine.
One simple example, you can think of that logistic growth, but
That's
it can
fine.
take.
That's fine. I don't need to know those details. There are many ways to implement that.
Yeah.
But but can you say a bit more? Okay, you are saying it depends, but what's the functional form? Is it monotonic? Is it non-monotonic?
So we are assuming that when the population size is less, it increases exponentially, but then decreases as the N increases.
Okay, fine. That's good. Okay, excellent. Group 4.
It will be monotonically increasing. I mean, but it kind of saturates off as the time goes. So the
What is
carrying capacity
monotonically
of the
increasing? What
population.
is monotonically increasing? The population size. Right?
Yeah.
Okay. Yeah. Group number 4 now, or 4 is done, or 4 is the one that's.
No, 4, sir.
4, yes, please. Yes.
Yeah.
We'll go in for 4.
Yeah. So if anyone wants to add into my thing, please go ahead.
Akshay, okay.
Can you see it?
Yes. Okay.
Yeah. So so apart from carrying capacity, so we did include a carrying capacity to limit for environment. But Nilay pointed out that if you were to colonize a given area with say 2 people as opposed to 100 people, the rate of growth initially would be slower when you have just 2 people until you establish a certain critical mass, and then you would experience it. So we tried incorporating that, and we ended up at the logistical growth model with like a lag phase. So if you were to start off with this, if you look at the red line, then if you were to start off with a higher population, you can very quickly go into the exponential phase and reach carrying capacity. But if you were to start off with a few number of individuals, then we tried accounting for an initial lag before you actually have that critical mass to gain an exponential increase.
Okay. Sounds good. Okay.
So I think, sir, I would like to add like a small point here. I think Akshay summarized it pretty well. The only thing is we started with the idea that we wanted to establish that the environment would affect the population more than the population would affect the environment. Now, it's not exactly like granted. I mean, just as a very far-fetched example, if you look at humans only, we affect the environment a lot in a very significant manner. But like here, the assumption is that the effect of the population on the environment is negligible, and therefore we can take care to be more or less constant.
Yeah.
I see. Okay, very good point. Very good point. Great. Nice. Okay. Next group.
Yeah,
Number
this is
5.
Raghuram here. So I'll
Yeah.
be sharing the screen. Maybe
Yes,
Rashi or Pawan can explain.
And maybe whenever people are speaking, please switch on your video so I'll remember over time who is, otherwise I'll not remember. Okay. And others can also see.
Yeah, Rashi, can you please go ahead?
Yeah.
Yeah.
I
So
mean,
this
if
was our
possible,
team
do
members.
switch on the, and at least the team members can switch on the videos whenever you're presenting. That would be great.
Okay. Yeah, I've switched on. So these were our team members.
Okay.
Yeah, Rashi will do the next explanation part.
Okay.
Yeah. Could you go to the next slide?
Yes, I can see.
Yeah.
Yeah. So basically, what we wanted to I'll speak about the assumptions that we made to our model first, because those are the things that were kind of like a roadblock to making the model more realistic right now. So in the given time, we took the assumptions that our R is constant with respect to time. In fact, the model works till a 2C carrying capacity, where C is the size of the population at the carrying capacity, and the fact that the model assumes that this particular nt plus 1 is not a continuous value, rather it's a value which is like an integer, not an integer, a natural number which changes with respect to time. So those are the basic assumptions that our model made. And then what we plan to do is that we realize the fact that as the model as the population goes closer and closer to the carrying capacity, the rate of change of the population should decrease slowly. It should not be exponential at that time. So this is what has been accounted into the fact that C minus NT by C, the rate itself, and then we multiplied it to the NT, which is the population at that time, and then we have used this model. The limitation with respect to the carrying capacity is due to the fact that if the population goes beyond 2C, we are observing the fact that we're getting negative population in our discrete model. So that's the reason why we made our assumption in this model. And what we expect in the population change with respect to beyond 2C is that it's going to decay, but how exactly it's going to decay is going to be a complex equation which we couldn't model for in the time limit. So if anyone has anything else to add.
I think that's fine. That's good. Okay.
Graph
Oh, you also
also.
did simulation. Oh, excellent.
Yeah. Pawan, somebody can explain.
Very fast. Excellent. No, I understand what's happening here. So basically, you have done this recursively, how this is changing over time, and then you found this curve. Very good. Nice. So next group number 6.
So I guess Sean, you can present first, then I'll share my thoughts.
Can you see my screen? Yeah.
Okay. Yeah. Please go ahead.
So we just decided to scale the inclusive rate of change by some term that accounts for competition and resource limitation. So we use this term here. If you can see my mouse, which sort of, as the population approaches carrying capacity, this term goes to zero on the rate of change. And this is sort of how we came up with it. So it's just sort of,
Okay. Sounds good. So it seems like many of you have arrived at very similar sort of equations, which might be partly because there is something very universal about my question.
So I'll also add something from group 6. Yeah, I'll just share my MATLAB screen because I haven't written anything down. Yeah, so I tried to modify the equation that you showed us in such a way that carrying capacity comes intuitively, and so that I don't have to introduce a different term.
Okay.
So my assumption was that as the population will increase due to limitation of resources, environment, whatever it is, the death rate should increase slowly and the birth rate should decrease, because birth rate, by birth rate I mean the number of offsprings who are going to be fertile adults. So I did a very like rudimentary simulation where I increased the death rate linearly
by 0.02 for every time step,
and decrease the birth rate linearly. Linearly doesn't work, I know now, because it just got exponential and collapsed. So my assumption is that the next step I would have done if I had gotten some more time is that tried to like modify D and R naught in such a way that they comes to an equilibrium rather than just increasing and fixing to the highest and lowest value they can achieve. I need to maybe think a little bit more about how I can like make a stable version of that, but yeah, that's something I'm trying to do.
Very nice, very good, excellent. Thank you. Group number 7.
Should I present or will Paras or anybody from the group present?
Anybody from the group can present.
Oh, so, yes. So here what we are presenting here, because R is the like a combined term that is for the birth and death numbers. So what we have considered, if we are below if the population is below the carrying capacity, so the R would be much greater than 1, as like if it is far beyond the carrying capacity. So as we go further, we'll reach near the K value, so R decreases and it tends to 1. And if we have an initial population that is much beyond K, so there R would be less than 1, means the death would be more than the births. And then it will the population will tend to again with a K where R is naturally 1. So that's what we have assumed.
Very nice, very good. Okay. Next group, group number 8.
Can you see the screen?
Yes, I can see your screen. Excellent.
So this is our basic equation.
So again, let me just remind you that in every group, whenever your group is presenting, please switch on your videos. So hopefully over the semester, I will remember all of it.
Yeah. So this is a basic equation that we've already come across, and we've tried to incorporate the resource limitation in R itself, because resource limitation affects health and thereby affecting birth and death frequency. So we've come with 3 different conditions, discrete levels, wherein if the original population is less than the carrying capacity, which is the highest capacity possible, plausible, then R is positive, which means that it gives a scope for the population to grow since there are more resources. This might lead to 2 different cases. The N might reach K, NT plus 1 might reach K, or it can overshoot. So in case of reaching K, then we want it to be constant at carrying capacity. In case of an overshoot, as shown here, not a very clear graph, but then we want it to again fall down to K. So that would require a second condition where R is less than 1 when NT is greater than K. But this again might lead to 2 different conditions. It can fall to K, NT plus 1 equal to K, or it can undershoot, go less than K, and then again there is an oscillation. So we've incorporated this, and then we wanted to incorporate the dependence on the difference between N and K. We want the equation to be such that if the population is very higher than carrying capacity, then we want the drop to be a little rapid. As in the drop in the population should be rapid, but if it is close to K, the drop will be slower. So we've incorporated this difference between K, a fractional difference. This is, we have divided by K for to get the fraction, which will account for the acceleration and deceleration of this oscillations. And to incorporate all 3 different discrete levels into one, we have come up with this final equation where we consider R is equals to 1 plus R naught K minus NT by K. Basically, we did these 3 and we found out that this equation incorporates all 3 different conditions. And then this R, when incorporated here, will give us the final equation as so. And this is actually equivalent to sigmoidal curve, but I'm like on differentiating this, we'll get the sigmoidal curve, which again is a good representation of involving resource limitation of population dynamics.
Okay, excellent. So which is the next group?
Is it group number 9?
Yes.
Hi, so I'll just share my screen. Is my screen visible?
Yes, yes.
Hi. So we have two slides here. The first one will be telling the thought process we had, like how we would design this equation if we had to, and the second one would highlight the information bias that we had. So Bharadwaj would explain the first slide. Bharadwaj.
Yeah. Hello. So so we try to modify the r in the equation dn by dt is r times n. First by seeing whether a polynomial function would explain this carrying capacity logic. So the first or the obvious thing it was to find a linear relation, which is shown here in blue. So the r will directly depend on k and will directly depend on n in linear fashion, and this red dot here will be the carrying capacity. So if the population is above k, then the rate is negative and it will come back to k, and if it is less, and it will increase to k. But then in certain populations, so for instance, we can see the growth rate to be much larger when there is no resource limitation, or when graphically if n is somewhere here, so very less values of n. Although I forgot to plot, so we try to do something like k minus n whole to the power m form. So when m is less than 1, what we get is the rate of growth would be much faster when there is very less population, or in the sense that when the population number is much away from the carrying capacity, much lower than the carrying capacity. But when it gradually approaches the carrying capacity, it's not just the population that caps out, but it's also the rate that diminishes at a faster rate. So this is the first, and I couldn't find a example for the okay. It's the second slide. So
I think we have covered the ground. I think it's fine because I am running out of time.
Yeah, sure.
So I'll request the last group to now quickly present what they have done. Group number 10, Sharaj, Kartikeya, Arshad, and then anybody from the group number 10? I can't hear you, Shah. You have to switch on.
Sorry, yeah, I didn't realize that. Yeah.
Okay.
So yeah, so I'll present for now, and the rest can add after I finish.
Sure.
So can you see my screen?
Yes, I can.
Yeah, so we decided to model the resources first. So we take a constant supply x naught and a consumption that's dependent on the population. So we have the resources present at time t equals x naught minus some constant into nt. And then we try coupling this with the population itself. We took r naught minus d, which was the earlier rate, like rate of birth minus the death, that depending on the resources available, that is k into xt. And basically, I mean, through these equations, we reach nt plus 1, which is some constant into the population present minus some quadratic term. So we see that this resource term decreases exponentially with, not exponentially, I mean linearly with the population. And at some point it will go negative, at which is when this population will start capping. Okay, will start capping, and at that point, even if you increase the population slightly, this it will fall down again because there are not enough resources, and the rate will be negative, because of which you have decreased population, and hence the rate goes back to positive. So it will basically saturate like the rest of them showed.
Okay, that's great, very nice. Thank you. So all the groups have presented now. That's really, really nice. Okay, so let me make a few observations. First and foremost, that I think every one of you got the sort of gist of the argument, which is that as population increases, there are the R that we defined cannot remain constant. Right now, resources will decrease, therefore the births and deaths cannot remain same forever. That's really absolutely right. And all of you have come up with sort of ways to work around it, and and quite remarkably, as I was also making this comment midway through, almost all of you have come up with a very similar equation form, and that could be for two reasons. One is that some questions have a universal answer, right? And maybe this is one of them, and maybe the second one is all of you have read the same stuff and you already know the answer to this question that I asked. Probably it's a combination of the two. Okay, so and while doing so, all of you have very nicely thought through how to add sort of biological realism into simple mathematical equations, and we have sort of very deeply thought through various ways of doing it, and different groups have done it in different ways. While a large number of groups have stuck to a single equation, a single variable, there was one or two groups which also wrote a separate equation for the resources and then incorporated them back into the equations. Those were all really nicely done. So a few observations I sort of have noticed is that many of you were trying to arrive at a sort of so I wanted this curve to look like the sigmoidal curve, right? Or I wanted the growth rate to be this when this happens. I wanted the growth rate to be this when happens, right? So in some sense, many of you wanted certain specific outcomes, and then you were writing the equation somewhat accordingly. Okay. Of course, that's as you can see, that's actually a very important component of modeling. But the only catch that one has to keep in mind is that what is it that the outcome that you are looking for? Do I want a sigmoidal population curve, and therefore I should write down the equations in some way? Is that what I am trying to do? Or is it that, let me think of the processes. What are the processes that are affecting the population birth and death? Let me not worry about the outcome. I just want to incorporate the processes as accurately as possible, right? So both of them will lead to equations. The emphasis on trying to capture the processes more accurately, and then therefore you arrive at an equation. That is one way of writing down an improved model of any type. The second one is, I want this outcome. I want the population versus time to look, this kind of initial exponential growth followed by a sort of, a saturating thing which looks like a sigmoidal curve. To achieve that, I already know this mathematics will help me. Therefore, I'm going to write an equation like this. So both of them are in some sense valid approaches when you're doing a mathematical modeling. But you must also remember that both of them have their own disadvantages, especially the second one. Because you are so focused on a specific outcome, what that means is that you often may ignore something more interesting because you're only so much focused on a specific outcome that you are looking for. Whereas a process-based modeling is often agnostic to what the outcome, right? Because I want to incorporate the processes more accurately, and therefore, in my opinion, is a more powerful method, especially when we are building theory. So when we are building theory, we are not constrained by how the world must look like. The purpose of theory is to sort of figure out, given that we know something about the processes, what are all the different possible things that can happen in the real world, right? So you're not necessarily extremely constrained by what the outcome must be. The focus must be on the incorporating processes that are important, and in a way that sort of is reasonably well founded. Okay, so remember this while modeling. So I understand, I'm using a different word from theory now. While modeling, you may sometimes need to be a lot more focused on the sort of more precise details of the outcome that you are interested in. For example, if I already had a graph of bacterial growth curve, or how the elephant populations grew and then saturated, then I want to make sure that the equations I'm writing actually capture that in the end. So understand this difference between sort of doing theory and also doing modeling. Modeling is often for a very specific data set in some extreme cases. Okay, whereas theory is sort of slightly broader sort of a philosophical approach, where we are trying to make a sort of a more general sort of a statement, and we are not necessarily interested in one specific aspect of data we are trying to explain. Okay, so with those general remarks, let me now sort of try to summarize in my own way what how sort of what every one of you have already said. Basically, let me just share my screen. I hope it's sharing properly now. Okay, so I'll make it full screen. So all of you recognize that when we began with this equation, there was an inherent limitation that R, which is a measure of the growth rate, was a constant over time, and that all of you recognized will not be a right thing to do. One common mistake when I ask people to model how they should change to account for resource limitation is that to make R dependent on time. But there is a problem with this. Should R decrease with time? Should it increase with time? It's not necessarily very evident. It really depends on what the resource will be at a future time, and there might be no way for us to forecast accurately. But one thing we can say is, since R is a measure of growth rate, and if you think that R depends on resources, right? We know one thing much more accurately than R versus time. What we do know is that R, if you were to think of it as depending on the population size, this should have a decreasing curve, and in fact this is what a lot of we have done. So this was the thinking I was trying to look for in many of your logic. So specifically what I was trying to look for was that the thing that R, which is a measure of net birth minus death or net growth rate, how does it depend on the population size? The population size is really, really large. This number must be basically close to 0, right? On the other hand, if n is, if the population size is really small, it can actually take the maximum possible value it can take. So we were calling it RM, right? So RM might be the maximum possible value. Okay, and as n increases, this curve basically has to reduce in some form as a function of nt. Okay, and that could be sort of a straight line. It could be more of a asymptotically saturating function, or it could even be something like this, right? It could also be something like this. Okay, now those details will those will depend on various processes that we have in our mind. Further understanding of processes at the detail that we are currently considering, it might be difficult to say, is it linearly decreasing or more gradually decreasing, or is it sort of convex versus concave kind of functions. So that might be a bit difficult to hard without thinking through the processes a bit more, but nevertheless we do all agree that R has to decrease with n, and what many of you have done is chosen the linear form. Okay, and let's and then have also thought about other factors like carrying capacity, which we have not defined in the course. First, we have not defined carrying capacity. What do we mean by carrying capacity? But you have used the concept, and how at carrying capacity the population must sort of come to an equilibrium and so on. Okay, so if you want to think of purely a modeling point of view, you must realize that this is the crucial graph, that R has to reduce with the total population of the total population size, because as total population increases, the amount of resources available to every individual will also reduce. Okay, and any of these curves actually captures that phenomenon, and the mathematical form we choose is often a matter of personal choice, to what we think is more realistic, to what is actually feasible, what actually is easy to solve. Okay, and in fact what many of you have done is choose R to be a linear function and have made some modifications. So what I will now do is let's now stick to the simplest form, which is R is equal to the simplest form, which is a linear form. Okay, if you choose R to be a linear form, okay, let me now use a different notation here. I've already used R0, right? This was really bad. RM, right? RM is the maximum value it can take. So let's say if we call the value of population at which the growth rate becomes 0, if that is if the value of population is k, then R will form, or will look in this sort of an expression. And if you incorporate this back in the equation above here, what you get is that nt plus 1 is equal to R times nt into 1 minus nt over k. Okay, for nt less than. Why did I write this specific condition here? As you all know, in this specific equation, if nt was greater than k, the second term here will become more than 1. So the R will become negative, and that is not allowed. So therefore, I'm going to restrict n to be less than k. Okay. Now, and many of you have incorporated additional terms to sort of account for this problem, and I think that arises from a very interesting confusion you may have had. What is the interpretation of k here, capital K?
Carrying capacity.
Okay, that is not right. Okay, I'm going to let you think why it is not right. I won't tell you right away why. It will be part of the assignment. Just think about it. So we will. I won't answer that right away. But that's the most common, mistake in this case.
Sorry, sir. Here in your graph, K is not a carrying capacity, right? As you are saying this.
Yeah, I'm saying it is not carrying capacity. I think some of you may have already figured out why it is not, but I won't, I will leave it as a small argument for you to make it assignment. Okay. So K is not the carrying capacity. K has a different meaning, and I will let you think and write about that in the assignment. Okay. So now let us do second part of the breakout exercise today. So let me, before we do, let me just say one thing. We could have chosen a different functional form here, which is decreasing, but we have chosen this as the choice that I have arbitrarily made, and that also seems to be the choice that many of you have made. Okay, therefore I have chosen this. We could have chosen more complex nonlinear forms here. Okay, so but there's nothing really very pristine about the choice that we have made here. Okay, so with that choice we have this equation, nt plus 1 is equal to rm nt 1 minus nt over k. Okay, so one very useful thing to do whenever you have a mathematical equation with a number of parameters is to see, can I get rid of some parameter values? This might sound really bizarre. Why do you want to get rid of some parameter values? If it is possible to reduce some parameter values without losing the sort of underlying biological features, it's useful to analyze the equations mathematically. Okay, now it turns out that in this case we can simplify it. Let me define x of t as nt divided by k. Okay, if I do this and then divide the entire equation by k, what do we get? I get nt plus 1 by k is equal to rm nt by k 1 minus Is it fine? You can see that this nt by k comes 3 times. Once here, once here, once here. What is this? This is xt, right? What is this? This is also xt. And what is this? This is x t plus 1. Basically, xt is nt divided by a constant. You know, in some sense, it has normalized x of t to 1 minus x of t. So we now have a simplified equation with only one parameter value Rm. Okay, so we had 2 in the previous equation. We now have a single parameter in the equation. This kind of process is called rescaling. So we have rescaled the population size by a parameter k, and in doing so, we have actually not lost any information. One can think of x as the population density instead of population size. Okay. So we have now a simple equation. So now, what do we learn from this equation? What can we learn from this equation? And that is going to be the next set of exercises we will do in the breakout room. Okay. So what will you do? So if we remember, we had we already knew what are the values that Rm can take, right? What are the values that Rm can take? Did we discuss this?
The non-negative real based on
Remember, Rm is not same as R. Rm is basically
the upper bound.
The upper bound for the number of offspring that the individual in this population has. So right now we don't know what exactly it is. Okay, so basically it has to be one thing we do know is Rm has to be greater than or equal to 0. Okay, and then we can sort of try to increase this value and see what happens. So here is a small exercise. All of you have computers accessible to right now. Okay, that's an assumption I'm going to make. And then what I would like you to do is the following. Okay, I'll set up a new page. So this is the exercise, the same groups when you assemble, this is what you need to do. Choose different values of Rm from 0 to 2. Okay, and when you go back in groups, you can decide how we will choose these numbers. Okay, and I would then do this simple iteration, and then I would like to see a graph of this type, how xt is changing over time. Okay, so now depending on the value of Rm, this graph will change. This will look differently, right? You can ask the following question: do you find extinctions? Right? Do you find equilibrium? I hope all of you understand the meaning of equilibrium. We will define it more carefully in the next class. And how does that equilibrium change? Okay, but we will do this for different values of Rm. When I go back to the very first model we wrote, another one, where is that? Okay. We looked at this equation, right? So here we had 3 cases: R less than 1, R equal to 1, R greater than 1. There were 3 regimes, right? Where there were 3 different types of outcomes possible: extinction, equilibrium, and then we can call it explosion or exponential growth. I want to see what do you find for this when you vary Rm from 0 to 2? Do you find similar 3 features? Do you find extinction, equilibrium, and again explosion, or will explosion be controlled? Of course, as you have guessed already, and this is a model that many of you have come up with, explosion should not happen, right? So I want you to sort of check these basic sort of basic phenomenon running this model. Now you don't have to, by the way, do simulations using R or Python. You can actually just use Microsoft Excel or Google Spreadsheets. So all of you know how to do that, to simulate this. I can just show you if it's not very clear to you. It's extremely easy. Okay, do I need to show it?
No,
yes, please.
Okay, I can
could you
do.
show?
Yeah. Let me just open a Google spreadsheet. Okay, I'm going to share my Google spreadsheet now. Okay, are you able to see my Google spreadsheet? Okay, so what are we interested in doing? We are interested in plotting how X changes with time, right? So in the A1, let me just write down the value of R0. Let's say 0.2. Okay, and this, let's say B is the column where I will look at X of t. Okay, and in the column in the entry B2, I will write down the value of population density at time, the first time. Let's call that 0.1. Is that fine? What's the maximum value X can take? Think about this. The maximum value X can take is actually 1. Because if X is greater than 1, that equation will become negative. Okay. Okay. So X can be between 0 and 1. Okay. Now I have taken this. Now what you do is you go to the second, the B3. Given this, can I calculate the next population? So basically, next population is equal to RM, right? What is RM? RM is, okay, let me just do this. RM is let's say 0.5. So A2 has RM. $2, I will tell you why I choose dollar, okay? $2, that's the basically value of RM times, what's the formula for finding X, next value of X?
Is X of t
into 1 minus xt, right?
Yes.
What is X of t now? It will be basically
0.1.
B.
Yeah, B
It will be B2.
dollar B2.
Right? And 1 minus B2. Is that right? If I calculate B2 is 0.1, 1 minus B2 is 0.9. If I multiply that with RM, I get the next population size. We all agree with that?
Yes.
This is basically the formula of R times X times 1 minus X. Is that right?
Yes.
So if I press enter, I'll get the answer. Okay. Now I want, what do I want next? I want the next population. So 0.1 has become 0.045. Okay. Now I want to know the next population size. How do I find that? That is same as this RM.
RM should change.
No, RM doesn't change. RM doesn't change. Okay. Okay, actually it should not be called RM. No, what did I use? RM doesn't change. Okay, I think I'm sorry. I think I have messed up a bit in the notations. I have not been using correct, very good notations. See, the thing is, the way you have now written the equation already accounts for the fact that RM is changing over time, right? Isn't that right? So once, so your equation, which is, if I go back to the, I have to unshade this slide, otherwise I will not be able to. If you remember the equation, X is equal to RM times xt into 1 minus xt, right? That already accounts for the fact that the R is changing over time. Is that right? So I don't have to change RM anymore. Okay, so now what I now need to do is I have to, how do I calculate this? It's basically 0.5 times 0.045 times 1 minus 0.045. Is that right? Do you agree this is the next population size?
Yes.
Does anyone not agree with this? From 0.1 I got this, from 0.045 I can get this. No, next population size. So all of you agree with this? Anybody has a question about this? Yes. Anybody has a question?
No.
No. Okay. So we got the new populations. Here is a trick though. I can't keep on doing this manually forever. It's going to take a really long time. What I can do is I can hold this corner and drag. It automatically calculates. Say, look, what it did was it took $2 times B3 into 1 minus B3. Look at this, $2, B4 into 1 minus B4. So what it has done is, when I have dragged, okay, it's always taking this part of the equation from the previous cell, whereas the coefficient from the A2 cell. Is that fine? So all that you have to do is write and use your Microsoft Excel or the Google spreadsheet to calculate how X is changing over time. So this is time 1, time 2, time 3, time 4, and so on and so forth. Any questions on this? Let me show it again.
So the
Let's
dollar was used for the, I mean, for not changing it. Is it?
See, if I had not used the dollar here, let me just show it right away. If I had not used the dollar, and then if I do this, what happens is this. So when the next cell becomes A3 instead of A2. See, it used this algorithm of iteration. It has now used A3 instead of A2. But if I use $2, that specific cell gets frozen in this drag operation. Is that clear to everyone?
Yeah. So should we plot this also?
You should plot this for your own sake. Okay, please plot this and then try to see what you find. Okay, you have it's 4:25 now. Unfortunately, I was hoping that we will have 1 hour for this, but we don't have 1 hour for this. So we are a bit time limited right now. But I'm just thinking how we can how many of you need to leave at 5 o'clock? Okay, if there are, so here is some 3 people have raised the hand.
I do have to leave at 5.
Okay, so let's keep our
too, sir.
goals. Okay, so let's keep our goals modest. What I would like to do for the next half an hour is, I will now basically recreate the breakout rooms. Do this exercise, plot this xt versus t, and see how it changes as a function of the RM. Is it fine?
So, like in the Excel sheet that you showed us, you are varying the xt, like the 0th time also, right? So, are we supposed to do that, or are we supposed to vary RM because it says RM 0 to 2?
So, I have shown you, I was just showing 2 odd cases, how results will depend on the initial. So, we call that initial condition, an initial population size, right? Will that affect the final results? Yes, I agree. That's also a very, very important point, and you must also try to do that. For example, here is the graph, right? So there are 3 things we can ask. So here is the first type of graph. So I can start with this xt and then see what happens to this. Maybe I can start here. Now what happens? Will it go like this here? Okay, so keeping RM constant for both of them, RM let's say is 0.2. And you can ask now a different question, which is, okay, let's say I start here, and let's say with let's say plot 2 graphs. Okay, let's say this is, now we can ask, this is for RM is equal to 0.4, maybe this is for 0.2. For the same initial population size, how will RM change your results? Okay, that is something would be very interesting to plot. And on the other hand, fix RM and see how initial conditions will affect your results. Does it make sense? 2 types of graphs. So
Yes,
just write this down here. It's very good that you asked this question. So the first question is, fix RM, plot xt versus t for different x0. Okay. Second question, fix x0, plot xt versus t for different RM in this range. Is that fine? So I'll just make one note. X0 must always be less than 1. Is that fine? So to your the 2 slides that you have made, right? Add these 2 graphs in 2 different slides as your results. Is that fine? And write any comments and comment on the results. And this year, if you are unable to complete by 5 o'clock today, it's fine. So you must complete this, convert your PowerPoint into a PDF and upload it before, let's say, can I say before tonight? Is it reasonable? The only reason I don't want to give too much time is I don't want you to, write a thesis on this. Okay, I just want you to think about this. Okay, so take the kind of same, you need to polish up your slides anyway. Some of you wanted that anyway. Do you think is it too restrictive tonight?
It's May, or how do we submit?
On Canvas, we will create a assignment and you can submit it. Or if tonight is too restrictive, we can make it tomorrow noon. Is that okay? Is that better preferred?
Yes, sir.
Okay. Okay, sounds good.
So one from the group has to upload.
Only one from the group. Please make sure that all the group members' names are very clearly written on the very first slide.
Do we merge the 2 different activities?
Yes, please. Yes, please. So it looks like when I create the rooms again, all the group members will be preserved. So it won't be a new randomization again. Okay. So you will be the same group when you go back. Any questions before you go to the breakout room? Okay. Okay, great. So we'll all go to I'm going to open the rooms now and we'll have a minute or so to join them.
So basically we have to do this until we see some kind of a pattern emerge, right?
Right now, make sense of the pattern of what you find in this range that I have described to you. Okay. Stick to R0 between 0 and 2 and work on that.
I was actually talking about the times to be specific. That I think we just wait until like something.
Oh, how long do
happens.
you wait? Absolutely, that's a good point. Yes. How long do you wait is a question for you to answer. Figure out.
Okay, thanks. Sir.
Okay, cool.
Sir, can you send the invite again because
Yeah, we're not getting.
Okay, we have to. Okay, somehow you're not assigned to any groups. Lakshay, tell me which group you were in.
Sir, I was in the 9th group.
Lakshay was in 9th, no? Okay. And then Akash.
I was in 2nd group.
Prakhar.
Sir, 3rd group.
Raj.
Group 4, sir.
Vivek.
Yeah.
3, 3rd group.
Abhishek.
Sir, 7th one, I think. Group
Chandan.
7. Yeah, thank you.
Chandan.
Sir, could you please assign me to a group? I wasn't present when the groups were being made.
Kartikeya, done. Yes, Kartikeya.
Sir, group 10.
Okay, done.